There we go. All right, that's better. Hi, everyone. Uh, Hello. So today, that is the. We don't need that. That is the daily activity for today. I just posted it. Hi. Um, Forgive the shirt. It is laundry day. Here at the McBurney household. I actually the dryer's almost done, so after the break, I'll probably have a button up on. But I do apologize in the meantime for the presentation. Anyway, so today we're going to pick up with algorithms. We're going to talk about asymptotic analysis, which is scarier sounding than it is, and it's an important concept to understand. From there, we will talk about searching and sorting techniques and how they relate to algorithmic analysis. So that's going to be the day. Let me just check my whiteboard camera real quick. It is a bit low. Sorry, my hand is attacking all of you right now. All right, that'll work. Okay. So with that, just some notes. Homework 0 and 1 are on gradebook. Homework 2 was due last night. We'll grade it over the coming days. We're expecting a few late submissions there. Homework 3 was posted yesterday. Webcat only went up this morning. And the reason Webcat only went up this morning was just we've had issues in the past, especially around Homework 2, where people get flustered and they end up submitting their Homework 2 to Homework 3. And the problem with that is that Homework 3 actually includes a lot of the tests from Homework 2. And so it will almost look right, except for a few things will be wrong, and people might panic as a result of that. And that's just because Homework 3 builds so tightly off of Homework 2. Um, so Webcat is up for Homework 3. To that end, from there, we have a quiz today. Quiz posted today. It's primarily on algorithms, which is what we've been talking about yesterday and into today. Finally, just some general reminders. The final exam is next Saturday. I have been told that it is okay for me to give it as a take-home exam for the duration of the day. However, it can't start earlier than 1 p.m. So that is to say, you won't have to take it explicitly between 1 p.m. and 3, whatever time it gave me. It will be available until midnight that night. Our goal being to grade that quickly, but just be aware, this is coming up on the horizon. We will get, so the exam should be graded, including the coding portion. I didn't check let me check, I'm just checking the overall average right now. I haven't had a moment to do so until right now. The overall stats for it, hang on, it's being slow. Yeah, so the median score on the exam was an 87.5. There's a pretty wide distribution, I would say. The standard deviation is 9.47, but that's a very high median, so I don't intend to do any additional curving. That includes the coding question. So the mean was about a B, like an 85. The median's always higher than the mean when it comes to these exams, just because there are more outliers farther to the bottom than above. Anyway, so that's kind of your logistics update. There's a quiz out today. Homework 3 is due Thursday. Homework 4 will be posted Thursday. It will cover recursion and concurrency, which we will cover over the next 2 classes, not counting today. Were any questions removed? No. No questions were removed from the exam. I think I'm removing one from a quiz, but I'll worry about that later. At what score do you understand the material sufficiently? I that's impossible to answer. And here's why. One, I haven't taught 2150, so I'm not familiar with exactly what threshold we want to. my view of this class is it is prep for 2150. And so if you do poorly on the midterm but well on the final exam, I think you're fine. I certainly, if you have a score lower than a C, I would be pretty concerned. If you have a score that is a low B, I mean, that's not to say you can't improve, but I would say that's still fairly good, relatively speaking, given the material, given the content of the exam. Will the final be a similar format? Yeah, pretty much the same format. It'll be longer, but by that it'll have more time as well. The final exam should be 2 hours long, based on how I've written them in the past. I plan to write it similarly. So that is to say a 120-minute duration, but as such it will also have more questions to fill that 120-minute duration. Any other questions? Is there a way to know what we missed on the coding question for future reference? So you should be able to see the feedback. If you look at your exam feedback, you should be able to see the feedback just within the question itself. Let me just make sure of that. It should be visible. Oh, it didn't have graders' comments. My bad. Oh, yeah, okay. Apparently, we didn't have graders' comments available, but I can fix that pretty much right now. Sorry, it's one of the many settings, one of the many checkboxes that you have to check. There's I'm not even joking when I say there's about 8. Okay, so that should be visible now. If not immediately, then within short order. Yeah. All right, so from there, today we're going to pick up with algorithms. So last time we started talking about this idea of order of complexity. Talked about constant time, linear time specifically. There's some other timelines that we're going to look at, but mainly the two that we spent the most time on. Constant time, no matter how large the problem gets, it takes the same amount of time. Things like simple mathematical functions. By simple, I mean addition primarily. From there, we have linear time. And linear time means that it's proportional to the size of the input in terms of how long something takes. We gave an example of adding to the front of an array list because you have to shift values. The larger your array list is, the more values you have to shift. And as a result, inserting at the front is linear time, whereas inserting at the end always takes the same amount of time, is constant time. This is why array lists are worse when you have to insert at the front than, say, linked lists. So the key to this is we want to talk a little bit about this thing called Big O notation. And the start of that, we talked about counting operations last time. But the start of that is this idea of the complexity. What is the complexity class? What is the rate of growth? That's the big term I keep throwing out. And the idea is that as the input gets larger, we compare algorithms by how quickly they grow, what their rate of growth is as n gets larger. So for example, later today we're going to talk about insertion sort. And then tomorrow we'll discuss merge sort. Merge sort is actually better, and we'll talk about why. And I can actually give a brief demonstration. Later today, we're going to talk about this file, which I have uploaded. You can already see it. You can already check it out, called Sorting Examples. And this shows 4 different sorts. We have a sort for what's called a bubble sort. We have what's called a selection sort. We have what's called an insertion sort. And we have what's called a merge sort. And we'll talk about merge sort later. Not today, but tomorrow. We'll talk about the 2 of these, insertion and selection, later. And I just want to illustrate something. I want to show you how long it takes to sort a very large number of elements with a selection sort. We'll talk about how this works later, so put a dog ear there about like what is a selection sort. We'll get there. But I just want to show you how long it takes. So I'm going to do a quick run. And I'm going to set up my run configurations. What I'm going to do is I'm going to sort 10 million randomly generated numbers. Oh, you can't see the... I'm going to sort 10 million randomly generated numbers. Those numbers are randomly generated between 0 and 20 million. So this is a pretty large sort. I'm sorting 10 million things. So let's apply that and let's run. And you'll notice that it starts sorting, and we'll keep an eye on when this finishes. It's not going to finish quickly, but we'll talk about how this works, what a selection sort is, and why it takes as long as it does later. But just recognize for now, it's not done yet. But the idea is we can compare algorithms. Remember, algorithms being a precise step-by-step set of instructions to solve a problem. We can compare them. Because it turns out that two people doing two things two different ways may produce different outcomes, by which I mean different efficiencies. For example, not all algorithms are made equal. If I were to leave my house by my car, there's two ways I could go. One is the back way that goes up Interstate 64 if I were going to my office, and then across, I think it's called 250, and then down into UVA from the back. The other way I could go is up 5th Street, turn left, and go through some back roads. Those are two different approaches to get to work. One of them will, on average, be significantly better. By that I mean it will have an average faster time. And I should always use the faster route. There's no benefit to using a slower route. Again, if time is the only factor we care about. So two algorithms that ultimately produce the same result, ultimately complete the same goal, may not produce the same efficiency. And that's the case with the selection sort. By the way, still not done. It's still sorting. We'll come back to that later. And so when we're comparing algorithms, we start with this idea of asymptotic analysis. That is to say, as things get larger, how does the problem scale? What is the rate of growth? And generally, the slower the rate of growth, that is, the smaller the rate of growth, the better the algorithm is. Doesn't mean the algorithm's always better. It just means at a certain point it gets better. For example, let's say that I have an algorithm that completes, so the amount of operations needed to complete some task is some constant d. I don't care what the constant is, 3, 5, 10. The point is some constant d times n, times the size of the input, plus some constant k. If n doubles, then f of n doubles. We talked about this last time. In a linear problem, if the size of the input doubles, the runtime doubles. If, however, we're talking a quadratic time, something that takes, say, cn squared plus q, then if n doubles, f of n quadruples. Therefore, the algorithm that grows more slowly, the linear time, is better. Now, here's the question, though. What if... Where's my blue marker? There it is. What if we have two algorithms? I'm going to say the first one, f of n, takes 10 times n plus 20 steps. And the second algorithm, g of n, takes n squared steps. Which of these is better? F of n or g of n? Make sure that's showing up well. Okay, it is. Which is better, f of n or g of n, based on what I've been talking about? f of n. Okay, but we just had someone say something that is absolutely correct. Depends. Why does it depend? Why does it depend? Depends on n, right? It's assuming n is large. Now, how we define large matters, but here's the thing. The size of n, if it is smaller than some value, then g of n is actually better. For example, let's say n were equal to 7. If n were equal to 7, then f of n is 70 plus 20, it's 90. Whereas g of n is 49. So look, in this case, n is better. But algorithmically, this algorithm is considered better. F of n. And the reason is as follows. If I were to graph these two things, and this is intentionally a rough graph, my first graph is going to look something like this. This is f of n. My second graph, by comparison, is going to start down here, and it's going to grow slowly. And so right now, this is g of n. It's better. But what will happen is g of n will grow more steeply. And somewhere here, this is around n equals, this would be like n equals 12, roughly. This is somewhere near here, n is 12. At some point, so let's plug in 12. This is 120 plus 20 is 140 versus 144. So after 12, if n is greater than or equal to 12, then f of n is less than g of n. This is true for all values of n, from 12 to eternity. Now, when n is less than 12, is it true that g of n is less than f of n? Yes, this is absolutely true. By the way, n can never be negative. Because we're talking about the size of a problem. A problem can never be a negative size. It can never have negative input size. But the point is, when n is greater than or equal to 12, plug in any number, f of n will be less than g of n. And in fact, the bigger n gets, the bigger this gap gets. So for example, if n were 1 million, well, 1 million squared is 1 trillion. Compare 1 trillion to 10 million and 20. 10 million and 20 is hilariously faster than 1 trillion. Right? This is the key, is that yes, it's true that maybe when n is less than a certain value, is less than, I forgot to write it up here, less than 12, it's true that g of n is faster. But from a standpoint of comparing algorithms, we will generally say f of n is better in this case than g of n, just because it has a lower asymptotic complexity. That is, for f of n, if n doubles, runtime doubles. For g of n, if n doubles, runtime quadruples. So while it is true that when n is less than 12, g of n is smaller, we basically don't care. We don't consider that when analyzing these algorithms. We only worry about as n gets larger. Are there any questions on this graph? Now, to be clear, if they were the same complexity order, we care about constant set. But because of this feature, it doesn't matter how big this constant is. Let's say this constant were 100. Okay, if this constant were 100, then the crossover point, where f of n starts being less than g of n, is much larger than 12. Much, much larger than 12. But we still don't care. Because the point is, no matter how big this constant gets, it will still be a constant. And that means that there is some value n, such that f of n from that point onwards is less than g of n. No matter how big this constant gets, that is true. Because of this fact, we actually don't even really care about the constant. And that's where it may get a bit strange to say, but this goes into asymptotic complexity. Let's compare rate of growth. Let's say that I have these algorithms. Now you may think, okay, so by the way, this is not square shaped. This is 20 wide by 250 tall. If you look at this, it looks like, okay, well, f of n is this blue diamond here. It's worse than log n, but better than n log n. Better, even significantly better than n squared, which you see here, which is better than 2 to the power of n, which in this case appears to be n cubed. So you may be thinking in this case, okay, so exponential is still better than n cubed. That is not true, though. Because if we zoom out a little farther, you'll see there's some point where this line, which is 2 to the power of n, or exponential, passes n cubed and becomes steeper. And that's not very far. That's at n equals 10, roughly. At that point, n cubed is better than exponential. And if we trend these lines towards infinity, this exponential just completely outgrows everything. So just to be clear, don't look at a small sample size and say one algorithm is better than the other. Because in this case, it looks like exponential is better than cubic, but if you zoom out, that's not the case. So this is why we care about big numbers. And so when we're looking at algorithms, we're going to use something called big O notation. And big O notation describes the complexity class of an algorithm. For example, when we're looking at these two functions, it is absolutely true that if these two functions were compared in a vacuum, f of n would be better than the second f of n. That is, the first one, or excuse me, the second one would be better than the first one. Forgive me, I misspoke. The second one takes fewer steps than the first one because the constants are compared apples to apples. But if I change this to n cubed, no matter how big these constants get, this algorithm is now worse. Because when this one doubles in size, it quadruples. This one octuples. So we don't actually care about the constants half as much as we care about the exponents, specifically of n. So that's what we're most interested in. And so, to this end, we would take an algorithm like f of n is 100 n squared plus 50n plus 7, and we would say that this is O of n squared. Now, this is not a function. All right, what we're saying when we say something is O of n squared is that its rate of growth is the same as the rate of growth of n squared. So we're talking again about the rate of growth. So if I say two algorithms are O of n squared, that doesn't mean those two algorithms are equal. That doesn't mean that one isn't better than the other. It just means that they both grow at the same rate. Roughly, whenever you double the size of n, you quadruple the runtime. By the way, still not done. Just pointing it out there. It's still running. So, whenever we have some algorithm like f of n, 100n squared plus 50n plus 7, we just simply say this is O of n squared. And if you don't know how to do it, it's, I believe, Control-Shift plus. Yeah. O of n squared. This means that it grows at a similar rate as any other quadratic function. So the most common classes, constant time. We say that is O of 1. That means that the problem does not grow. It does not get larger. It is constant even when the size of n increases. Something is log of n when it's logarithmic time. And here is the easiest example I can give. I am going to write, and my keyboard is very loud. So here, like, You can hear my keyboard typing, right? Okay, so you know I'm not going to cheat. I am going to write a number on this notepad file off screen. This is a number between 1 and 100 inclusive. I will give you hints whether that number is larger or smaller. What's the first number you should guess? $50. Okay, 50. The number is smaller. The number is smaller than 50. What's the next number you would guess? 25. Okay, it is larger than 25. Again, try to play this perfectly. What's the next number you guess after 25? I said larger than 25. And also, it's a whole number. You can only guess integers. The number I have is larger than 25. 33 is not the best guess. 38 or 37. Both are just as good. Again, saying you have to pick integers. Let's say people guess 37. It's larger than 37. Okay, what's the next one you would guess? Let's see how we do. Well, 37 to 13, or 37 plus 13 is 50. Half of 13 is 7. So 37 plus, yeah, you guess 43 or 44. Both would be fine. By the way, the number, I'm not going to keep playing, but the number is 49, is what I wrote down. And I intentionally picked one less than 50. The point is, that type of game, that guess a number game, higher, lower, what you're doing, and we'll talk about this later, is dividing the search space in half. The number of guesses that it takes to play that game, guess a number, is equal to the log base 2 of n, where n is the number of values available. So 1 to 100, there's 100 numbers. In a worst case, if you play perfectly, it will take you 7 guesses. If I go to 1,000, it will only take you 3 more guesses in a worst case. If I go from 1,000 to 10,000, and in worst case, it will only take you 14 guesses. Go up to 1,000,000, only 20 guesses. And if you graph out the log, it looks like this. It is always growing. It is forever growing. But, and I'm not the best artist, so let me make sure it's always growing. It's always growing, but it is forever growing more and more slowly. That is, as n gets larger, it grows more slowly. And if an algorithm is log runtime, that means by doubling the size of the input, it only takes one more step. This is incredibly efficient. We'll talk about how binary search is significantly more efficient than a linear search. A linear search would take linear time. That is, if you have to visit every element of a set. So, for example, finding the minimum of a list of numbers, that minimum would take linear time to find. If I double the size of the list, I have to look twice as far. There's log linear time, and that is going to be O of n log n. And we'll get to some practical examples of that today and into tomorrow. Quadratic time is a poor sorting algorithm. And an example of a poor sorting algorithm that's quadratic time is selection sort, which, by the way, still not done. Still running. My computer's actually, the fan just kicked on, so it's working really hard on this. Then from there we have cubic time, and then we have exponential time. And there are many important problems that we don't have better than exponential time solutions. Exponential, though, is the worst. These are arranged from most efficient, so the best algorithms, to the worst algorithms. And whenever given a choice, you should always pick algorithms that are higher on the list. So what does it mean to say something is O of n squared? It means that the function grows at the same rate of O of n squared or more slowly. This is an important point. What we are saying when we say a function grows at O of n squared is that it is not worse in terms of a growth time than O of n squared. By that I mean, if I had some function where I said that the rate of growth, the number of steps you need, which, by the way, this is actually true for a selection sort, the number of steps you need is defined as roughly n squared, or 1/2 of n squared minus n. This is roughly the runtime. For simplicity, I can say, okay, this is less than half of n, or this is less than half of n squared, right? Because if n is always positive, then I can just basically remove this term and not worry about it. And this clearly grows at the same rate of O of n, because I could just say that this number is always less than n squared. So the idea of big O analysis isn't saying that this is exactly the runtime. For example, let's take two algorithms. I have f of n is n cubed plus 7n plus 1. Well, I can say that this value is less than n cubed plus, well, less than or equal to, I'll say, 7n cubed plus 1 for all values n greater than 1. Or let me make this n cubed. Because if I plug in any number greater than or equal to 1, then that will be greater than or equal, this term will be less than or equal to this one. Just because I've raised the exponent. I can now say that this is equal to, it's 1 plus 7 plus 1, 8n cubed. And this is trivially O of n cubed. Because with O of n cubed, we're not saying that n cubed is better, we're saying some constant times n cubed plus k is greater than or equal to 8n cubed. Which is true. I can very trivially say, if c were 9, that would be worse than 8n cubed. So when we're saying this, understand that how we don't just look at this and say, okay, the largest term is n cubed, therefore this is O of n cubed. Yes, you can take that shortcut, but this is the mathematical underpinning of that. I'm not going to make you do this on an exam. I will, however, make you do something like look at this function and say, well, yeah, that's O of n cubed. I just want you to understand that there is a mathematical underpinning. You're not going to need to know it in this class, but it's worth knowing. So there is some function, c times n cubed plus k, that is greater than or equal to f of n for n greater than some number, x. That's what O of n cubed means. By that definition, however, g of n, which is just n squared, this is also O of n cubed. It's also O of n squared. It's also O of n to the fourth. All this means is that it's the big O means that the function is as efficient as O of n cubed or better. So technically O of n squared is most tightly, this is the best thing to say, it's O of n squared, but it is true that it is also O of n cubed and O of n to the 4. This function is most tightly O of n cubed, but it is also O of n to the 4. This function is not O of n squared. So any function I can say is as efficient or better than its largest exponent or higher, but I can't say that this function is O of n squared because of that n cubed term. Are there any questions about this? So this is the best answer, but it's not the only answer. All these answers are correct. And O of n to the fifth would be correct. And even O of 2 to the n would be correct. It's just, this is the best answer. This is the most tightly fitting. We're not going to, on the slide, you'll see something. Why is it not the only answer? For the same reason I just said. When I say a function, so again, if I say, and notice I'm not saying f of n equals. If I say f of n is O of n squared, that means there is some function Cn plus k, Cn squared plus k, such that this statement is always true for some c and some k, with n greater than a certain value. If f of n were just 5n, this would be true. If f of n were 5n squared, this would be true. But if f of n were 5n cubed, it would not be. So, if a function is O of n squared, it is also O of n cubed. Because if this function were true, it would also be less than or equal to some d times n cubed plus L. Different constants, this would also hold true. So if something is f of n squared, it is also, if something is O of n squared, it is also O of n cubed, O of n to the fourth, O of n to the fifth, O of n factorial. All those are true. But the most tight answer, the most tightly fitting answer, is the best. So for example, if my function were f of n equals x squared plus 1, it is most tightly fitting to say f of n is O of, sorry, I should write n squared, O of n squared. This is the best answer, but it's not the only answer. For that reason. It just means that there is some function of n squared that is always greater than f of n. So that's why it's not the only answer. So it's an upper bound. It is a function that is always greater than it. Notice again we say some algorithm is O of n. We don't say it equals O of n squared. I want to make sure people don't do that. Now, if you're looking at big theta is the best answer. That means that it grows at exactly the same rate. So technically, this function n squared is also big theta n squared. But this means that it's a bit more complicated. This would mean that there's some constant a n squared plus b that is less than or equal to f of n, and with different constants, less than or equal to n squared, cn squared plus k. Don't worry too much about the mathematical underpinnings. You'll go over this more in 2150 and then in algorithms. Just understand that there is a difference between big O and big theta, but for this class, we're only going to focus on big O. So big O means it always, with some constants, overestimates. So again, that is to say, while it's more precise to say something is n squared, with big O, it would be but no worse. So any function that is big O n is also big O n squared and big O n cubed and so on. So O of n squared is an upper bound. There's these two others. Don't worry about these for the sake of the class, but just be familiar with the fact that they do exist. So, it turns out that these big O notations can be used to make pretty good estimates, specifically as n gets larger. When n is small, we'll get kind of large error rates in the estimation to the runtime, But as n gets larger, our estimations will get more and more accurate. So again, an algorithm is better if it has a smaller rate of growth. So again, we talked about this. This is the same idea as before. If we had two algorithms, n versus half of n squared, at a certain point, the n algorithm becomes better, and it never gives that lead up. It's always, n is always going to be better now that n is greater than 2. So it is not true to say a big O n squared algorithm is always worse than a big O n algorithm, but it is worse as n gets larger. That's the key. So again, we're talking about the asymptotic behavior of large problems. That is, as n gets big. We're talking about the rate of growth. And so, constant time's always the best. Logarithmic time is the next, then linear, then log linear, then quadratic. Speaking of quadratic, it's still running. And then cubic, and then exponential time. So some examples of constant time. Push and pop on a well-structured stack. I should say a well-structured. You can design push and pop to be inefficient, but you wouldn't need to. There are ways to do it where it's efficient. So push and pop stack should always be constant time. Insert remove should always be constant time. The conditional statement for a loop, only the conditional, evaluating the condition, whether or not to enter the loop, that is constant time. The loop itself is not constant time, but the conditional statement is. Declaring variables, that is creating variables, is constant time. Assigning variables is also constant time. Logarithmic time, we'll talk about a binary search later, and then later on in the course, that is next week, we'll talk about binary search trees. For a balanced binary search tree, some operations are log time. Linear time, traversing an array for any reason, whether that is finding the minimum, getting the sum, getting the average, finding the median. You can, by the way, do a linear time median. That's something you'll learn in algorithms. These are all linear time. They involve visiting every element of the list. That's a linear time. So for instance, the array list contains function actually is linear time, because that contains function loops over all the elements of an array list to check whether or not they're equal to some element. Log linear time, we'll talk about merge sort tomorrow, and that is log linear, whereas selection sort is quadratic. Finding duplicates in an unsorted list, that is quadratic. Anytime I need to loop over a list of elements and compare it to every other element in the list, that is a pairwise comparison. So if I have one list and I'm comparing every element to every other element, that's n squared. Exponential time, things like Towers of Hanoi, if you're not familiar with, we'll talk about tomorrow. Things like recursive Fibonacci solution, generating permutations of n symbols, that'll make more sense later, we'll talk about that. Anyway, so these are our complexity classes. So now let's do a quick little exercise. We're going to do this before our break. I'm going to show you a piece of code, and I want you to tell me the runtime complexity. And I want everyone typing in Twitch chat for this. Everyone. If you don't know, guess. And if you're wrong, there's no problem. But by taking the initiative of guessing and then finding you're wrong, then you can learn. And that's the goal here. So with that, what is the algorithmic complexity of this code? This is a function that takes in an array and returns the first value. In big O notation, what is the asymptotic complexity class? All right, I'm waiting. Everyone's got to type. Wow, there's only 11 people in the class. Constant, that's fine too. I'll allow that. Still waiting for more people. All right, there we go. That's good enough for now. constant time. It is indeed constant time. And that's because getting any index of an array, it doesn't matter what the index is, getting any index of an array is constant time. So if my array were size 1,000,000 and I wanted to get the 1,253rd, I could do that just as fast as the 1,254th or the 8,900th. Getting any element in an array is constant time. What about this one? This random number generator. What is this? No one has typed yet. There you go. Starting to get some people typing. Okay. So most of you said constant, and that is correct. This is constant. One, there is no input. There is no input to get the size of, but this always will take the same amount of time. This is constant. It doesn't matter how big your program gets. This is constant. It is not linear. Here's one. Get a random. This gets a random element from an array. This one is also constant time. And that's because getting any index from an array always takes the same amount of time. Doesn't matter how big the array is. And this is just simple mathematics, so it's constant time. Sorry about that. All right. What is the Thank you. What is the asymptotic complexity of this program or this function? Where n is the size of the array, what is the asymptotic complexity? I'm going to wait for a lot of people to type. Now keep in mind, I'm not doing I++ or I-. I'm doing I-3. Does that change anyone's mind? Or is maybe me just highlighting that a red herring? This is linear. This is linear. Because even though we're stepping by 3 through this array, it doesn't matter. It's no different in theory than if we step through by 1. Because if I double the size of the array, I still have to visit twice as many elements, even though I'm doing I-3. So this is still linear, still O of n. Linear or O of n. So even though, and you can read over this updated, even though it's I-3, this is still linear because, again, if I double the size of my array, I have to visit twice as many elements. All right, what is the asymptotic complexity of this code? This is some hypothetical sorting algorithm. What is this one going to be? And use, if you can either type it out or use the caret for exponents if you feel you need them. Getting some O of n squareds here. Give me 1 second. I'm back. Sorry about that. Right, O of n squared. And that is O of n squared because this is a pairwise comparison. I am looping through the same array twice, but it's a nested loop. Now, I want to be clear. This is only O of n squared because the for loops are nested. If the for loops were not nested, this would be linear. It's only because the loops are nested that this is quadratic. We focus on the for loops, and it's O of n squared. This one, what is the asymptotic complexity of this code? This is also O of n squared, because again, it's a nested loop. Now, it doesn't mean that all nested loops are that. We'll get to an example later that might trick you up. But here's one. What is the asymptotic complexity of this code? What is the asymptotic complexity of this code? See one answer so far? Exactly. O of n cubed. Exactly. You guys are nailing this. Awesome. O of n cubed. What is the runtime complexity of this one? What is the runtime? This one is a bit trickier. I'm seeing an O of n in there, but mostly O of n squared. So the key is to understand that these two loops are separate. And this one is a nested loop that visits every element of the array. This one is a single loop. So it turns out that this is n squared plus n, but n squared plus n is big O n squared. So this is n squared. Because the loops are not nested, they are separate. So it is not n squared times n, it's n squared plus n. Here's one. Anyone want to wager here what this is? What is the big O complexity of this? I highlighted a very relevant part of the code. This one's tricky. This one is indeed logarithmic. Log base 2 of n. I should note that as programmers, whenever you see log n, if you're a programmer, you assume log base 2. I should note, this is not exponential, this is logarithmic. So, we generally assume log is, and it's control plus, I think. Yeah. Generally, this 2 is what we assume. I should note that all logarithms are proportional. So log base 2 is directly proportional to log base 100, for example. It turns out to work out that way. So it doesn't actually matter what the base is, but we generally assume the base is 2. So if you just say log n, everyone will assume you mean log base 2 of n. And that is correct. It is logarithmic. This one's a bit trickier. I'll let you kind of look into it, read the text later. I do want to get this done, and then we'll do our break, come back and talk about searching and sorting. What is the asymptotic complexity of this code? What is the asymptotic complexity of this code? What is it? Okay, I'm seeing a couple O of n's. Someone stuck in an O of n squared. Oh wow, the minority opinion is O of n squared. Well, that must be wrong, right? Or maybe my voice is carrying some really heavy sarcasm, and maybe it actually is right. Here's the trick. This is not constant time. The contains method is not constant time. The contains method on a list is O of n. Now on a set, it can be, on a hash set, it's constant time. But on a list, this is O of n. And so because of that, we have something that takes n steps nested inside of a loop. So this is actually O of n squared, because contains is not constant time. So with that, this is uploaded. You can go and take a look at it. I think there are more examples in the reading that you can practice with. This is something you could expect to do on the exam. But we're going to take a 10-minute break. We're going to come back, reset, and now talk about searching and sorting, and we'll relate that back to algorithms. But before we go, it's still running. Let's see if it finishes during the break. We'll be back in 10 minutes, 2:07 p.m. We'll be right back. Oops. All right, we're back. Hello. I actually got. So this is cool. I got a Stream Deck in the mail just now. That I'm at just because I'm going to be teaching online for a while. So I got a Stream Deck. So I'm going to try to set this up for tomorrow. I just dropped it and broke it probably. No, it's fine. But I'm looking forward to playing around with that, seeing what it does. Looks cool. Anyway, should be fun. Hopefully makes it easier to keep the transitions all together. But with that, so, by the way, it is still running. Man, that's been running for over an hour. And it is running. It's using a bit of my processor. I mean, I can show you right now. It's using effectively all of one core on my computer. So well, I'll answer that. I'll answer that after class. If you ask after class, I'll tell you what the Stream Deck is for. But notice, like, OBS, which is recording me right now and pushing it online, everything, that's only taking up 3.4%. By comparison, Eclipse is using up quite a lot right now. But it's still not done. Why is that? Well, let's start by talking about searching and then say how that relates to sorting. So, turn my webcam back on. So here we go. So again, just a reminder, these are the common order complexities. We're going to be talking about primarily these four. So we're going to talk about a binary search, a linear search. We're not going to get to the best sorting algorithms today, but we are going to talk about these, the quadratic time algorithms. Quadratic time algorithms like this one that still isn't done yet. So, a way to think of runtime complexity is if let's say I have 1 second to complete a task, and that task takes n steps, and I can do 1,000,000 operations per second. So if you give me 1 second to complete a linear time task, I can complete it provided n is 1,000,000 or less. If you give me a day, I can do it provided n is, and this is 84 billion. In a day, I can do that. You give me a year, that would be 31 trillion. Again, assuming I can do 1,000,000 operations a second, which, by the way, is very low, I should note. If you gave me a century, I could do about 3 quadrillion. So really, really big numbers. Is O of n factorial worse than exponential? Yes, and we'll talk about that not today, but we'll talk about it a bit later on. So if you gave me this unit of time, a second, a day, a year, or a century, and you gave me an algorithm that could operate, or that scaled at log of n, this tells me the largest n that I can do in that amount of time. So if you gave me a problem that was quadratic, I could only do an n of size 1,000 in a second. So this is 1,000 times slower than linear. If you gave me a day, I could only do about 300,000. This is getting way smaller than n. Gave me a year, I could do 5.6 million. Gave me a century, 56 million. Now, just a reminder, this algorithm is n squared. Now, my computer works pretty fast. It does several billion operations a second. But the input size of this is 10 million. And just a reminder of what this slide says, if I had a year, I could, at 1,000,000 operations a second, 5.6 million is the most I could do in a year. So this algorithm, I don't think it's going to finish today. In fact, I know for a fact it won't finish today. It will not finish today. I'll prove the point by leaving it running. It won't finish during class. So now, let's consider two problems where this algorithm technique applies. I'm not, by the way, you're not expected to memorize this. This is just designed to help be a visualization task. So, two important problems, searching and sorting. The idea of searching is I have a collection of stuff and I want to find something. The idea of sorting is that I have things out of order and I want to put them in order. And the two are actually quite related. So, let's start by considering, let's say you were in the Harry Potter universe and Professor Snape says turn to page 394. By the way, I've never read or watched Harry Potter. I don't have any problem against it. I just haven't gotten around to it. When I have kids, I probably will. So the first, sequential sort, which is also known as linear search. Sequential search or linear search would be used if we wanted to just go through an element and look for something. So, for example, let's say I had the following array or list, or however you want to think of it. In this case, we'll say array, but it would work just as well with a list. Let's say I had the following elements. I had the following elements. 5, 15, 17. Let me add some more values over here. 1, 4, 19, 22, and 27. Let's say this were my array. A linear search would simply be looping over the values. So I check here, that's not, let's say I were looking for 19. I check at 0, that's not 19. 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 That is 19. And then I would return, my indices are 0, 1, 2, 3, 4, 5, 7. I would return 5 because 19 is at index 5. The point of searching is to return where something is. Does this make sense? Now, what if I were to search for 23? Well, if I were to search for 23, that's not 23, that's not 23, that's not, and then I've reached the end of the list and I never found it. So if I was searching for 19, that would return 5. 23, I still have to return a number. This function returns an int. I can't return null, so I would return -1. This is called a sentinel value. And it basically is used to indicate the item was not found. And that's because -1 is not an array index that exists. In Java, there is no array that ever has an index -1. Now, if you've done Python, yeah, -1 is the last value, but we don't have to worry about that in Java. -1 is not a valid index. So that's designed to tell us, like, hey, you know, I didn't find the value. That's a linear search. What is the runtime complexity of linear search? Based on what I just said, what is the runtime complexity? My marker's dying. It's not showing up well at all. I'll need to get new dry erase markers. I'll do that for tomorrow. What is the runtime complexity of linear search? It's O of n, exactly. It's linear. It's linear time. All right. So in this case, we have really two possibilities. Either the value is present, in which case the best case is 1, it's the first value we find, or the worst case is n, or the average case is n over 2, which is proportional to n. I don't want to say equals, I want to say is big O of n. So, if the item is present, we say it is O of n. Is it possible that it will be the first element and we don't need to go to n values? Sure. But the worst case is O of n, and we tend to evaluate algorithms by their worst case. The average case is also O of n. If the item is not present, however, In order for us to ascertain that the item is not present, we necessarily need to loop through each of the values, and that takes n steps. So in this way, a linear search is O of n, but that's not the best way to search for things. For example, if I said, this is Steven Erikson's The Crippled God. It's Malazan Book of the Fallen. Malazan Book of the Fallen, it is for people who like Game of Thrones, but think it doesn't have enough characters and complexity, and it needs more. It's like Game of Thrones on crack, is what I can basically say. Anyway, this is my thumb. So this book is thick. If you told me open to page 594, I would not go, all right, that's page 1. Okay, that's page 2 and 3. That's 4 and 5. 5 and 6. 7 and 8. Nobody would open a book that way. What would you do? You'd open to the middle. Okay, that's page 574. I need to go to the right. You go to the middle of the right half. That's 812. I need to go to the left. You go to the middle there. That's 648. I need to go to the left. And so on. You would narrow down your search space in order to find it. By the way, great book series. Very, 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 very hard to get into. The first book is not great, admittedly. But Malazan Book of the Fallen, if you're looking for a fantasy series that's going to take you 5 years to read. Anyway. Because all the books are that thick. Anyway. There we do a binary search. And the idea of the binary search is that we have some midpoint and we search. So we first go to the mid. We say, okay, go left or right. And we keep finding the midpoint and narrowing it down. I'll type it. Malazan Book of the Fallen. I should note the first book is very hard to get into because it just starts throwing proper nouns at you without defining them. The first book took me a long time to read because it was hard. Second book is the best fantasy book I've ever read. It's really good. Third book was even better. Second was the best I read at the time, I should say. Anyway. So the idea of a binary search is we narrow it down. It's like searching through a dictionary or a phone book. Like anyone does that anymore. But you probably learned to do it, right? You go to the middle. You say, okay, I need to go either left or right. So let's apply that to our whiteboard. Let's search for the same two values. Let's search for 19... actually, I'm going to search for 17 instead. So let's search for 17. The way I'm going to do my binary search is I'm going to define a low, which equals 0, and a high, which equals 7. And I'm going to assume that my value is somewhere between low and high. Now, obviously, this is true, right? It has to be in this array, and I'm including both low and high, in between low and high inclusive. If I were looking for 17, I'd first look by finding the middle. The middle is low plus high divided by 2. So 0 plus 7 is 7, divided by 2 is 3. So I'm going to start looking at index 3. I'll call this my mid. And I'm going to say, okay, 15. If I'm looking for 17, then 17 must be to the right of 15, because this list is ascending order. And so because of that, I'm not going to look anywhere to the left, because this value is not 17, and therefore none of these values can be 17. Watch 77 has a great question that I'm going to get to in just a second. So, then what I do is I say, okay, if it's not any of these values, then my low is going to become my mid plus 1, so low is 4. So now I find the mid again. 4 plus 7 is 11, divided by 2 is 5. This is my mid. Well, 19 is greater than 17. So it can't be here, and it can't be here either. So I'm going to update my high to be mid minus 1. So my high becomes 4. And I don't need these values anymore. Then from there, oh look! Low plus high divided by 2 is 4, and look, right there, we found 17. But the question was asked in chat. What if the list is not sorted? That is correct. This list must be sorted for binary search to work. If this list is not sorted, you cannot do a binary search. The results will not be accurate. I'll show an example of that soon. But now let's look through the same array for a value that's not there and see how that works. Look through the same array for a value that's not there. 1, 4, 5, 15, 17, 19, 22, 27. Let's say I'm looking for 8. Well, if I'm looking for 8, if this is my target, then I'm still going to have low be 0 and high be 1 or 7. I find the midpoint, which is 3. Then the low is 0, high is 7. 15 is greater than 8, so it's not here, and it's not any of these places. Therefore, I update and I say high, excuse me, is going to equal mid minus 1. So high equals 3, and then I repeat that process. Now I find the high is 2, not 3. Then I repeat 0 plus 2. The mid is 1. Well, that's not 8. 8 is greater than this, so I cross out that and this. Then I make low equal to mid plus 1. Low equals 2. Now I keep repeating this. I find the mid. Mid equals 2. I check, and this is not 8. So I cross this out, but then I say, okay, well, this should be, 8 should be greater than this, so let's look to the right. In order to look to the right, I make low equal to mid plus 1. Low is now 3. But now I have a problem, right? Because low is now greater than high, and that doesn't make sense. So if low at any point is greater than high, then the value cannot be in the array. So this is my loop exit condition. I exit if low is greater than high. So by that, I design my loop as while low is less than or equal to high. That way, if I exit this loop, having never found the value, I can just return -1. So let's actually take a look at code for this implementation. Did I just break my marker? No, I'm good. So here is actually, by the way, still not done. Still not done. Here is code implementation of a binary search. So while low is less than or equal to high, if I exit the loop, that means I never found the value, return -1. Otherwise, I calculate mid, low plus high divided by 2. If the mid value is my target, is the thing I'm looking for, I return that value. Otherwise, if the mid is greater than my target, that means I need to search to the left. So I say high equals mid -1. Else, if it's not equal and the mid is not greater than the target, then the mid must be less than the target. I look to the right, and so I say low equals mid +1. And I initially just say low and high are these values. This is a working binary search. But, as Watch77 mentioned, this only works if the array is sorted. If the array is not sorted, it will not work. Quick demonstration of that. I can do a very, very quick demonstration. Let's say this were my array. 17, 2, 13, 8, 19. This 8 is out of order. It's not this array is therefore not sorted. If I did a binary search for 8 on this array, I'd go to 17, and I would say, okay, this is my mid. Well, if I'm looking for 8, then I necessarily need to look to the left. So I'd cross out all these values. Notice I crossed out the value I'm looking for, because I did a binary search. So if the array is unsorted, you must do a linear search. You cannot do a binary search. However, if the array is sorted, it is almost always more efficient to do a binary search, and dramatically better. Dramatically better to do a binary search. If it is sorted. How much better? Well, let's go back to that slide at the beginning where I talked about the number of operations that you could do given a fixed amount of time. If, let's say we had a dictionary of n words, that would be log n. I could, I could in 1 second determine whether or not a word is there in a binary search if I had 2 to the power of 10 to the power of 6 words. That is 2 to the power of 1,000,000 words. Is it so much more efficient to do a binary search that is worth sorting a list than searching? Depends. How many words are you looking up? The reason for that is sorting takes much longer than a linear search. Sorting takes much, much, much longer than a linear search. Again, sorting can take a long time. It's still not done, by the way. If, however, I were going to look up tons and tons of values, then I would do that. Can we also use a hash table? So with a hash table, yeah, you could use a hash table. The hash table would do like the hashcode function. The thing is, though, in this case, we're assuming we have an array or a list structure. Because it turns out we need those. We need this concept of order, first and last, enough that we tend to use lists. Now, if your dictionary were a set, then that would be constant time. But in this case, we're assuming it's a list. If we do a linear search, our dictionary can only be 1,000,000 words long for our spell check to take 1 second, which there are more than 1,000,000 words. But if we do binary search, if our dictionary is sorted, we can do substantially more than there are words. 2 to the power of 1,000,000 is hilariously big. There aren't 2 to 1,000,000 particles on the planet. And by particles, I mean subatomic particles. So just kind of keep that in mind. So log is better. Binary search is better. In a best case, binary search is still 1. Sorry, I should delete that. In a worst case, it is log of n. In an average case, it's log of n. So again, you should always use a binary search if the array is sorted. But if it is not sorted, you can't do that. Now, this is not the in-class activity for today. I thought about doing this, but I decided it's a bit too simple. Anyway, that's a binary search. So think of it like looking through a dictionary. Again, the code is more complicated. You know, this is a binary search. There's a bit of complicated code to it. This is a linear search. Right? The linear search is much simpler. Binary search is definitely more complicated. But the binary search is more efficient if array is sorted. If array is not sorted, you cannot do a binary search. So that's why sorting is important. Sorting allows us to do binary searches and be dramatically more efficient. This is why human beings sort things at all, like as a species. You know, the library is sorted. Why? So it's easier to find books. I mean, it's why we sort things. So the question now is, okay, we know how to search for something, but if we were given an unordered list of stuff, if we were given some unordered list of things, how could we put them in order? And we've actually already talked about this to some extent, right? We talked about comparators and comparables and collections.sort, right? But how do those work? Well, there are some sorting algorithms that are more straightforward, and we're going to talk about those today. Insertion and selection sort. There's also one called bubble sort. And these are O of n. And as you can tell, they don't seem particularly efficient. I'm going to go ahead and stop this sorting algorithm. I gave up on it because selection sort was just taking too long. Now, it says selection sort is O of n squared, and merge sort is O n log n. Well, that seems smaller. I wonder how much smaller it is. It doesn't seem that much smaller, does it? Oh well, let's go ahead and run a merge sort. Let's see how long the merge sort takes. I have this argument system set up. Don't worry too much about exactly how I'm running it. Just... Alright, so anyway, the merge sort will take, a little bit of time, and it's done. It's done. It's over. It's sorted. Let's try that again. So as I was saying, the merge sort can take a little bit of time, and it's done. Selection sort would not have finished today. Merge sort finished in less than 2 seconds. N log n is not a little bit better than n squared. N log n is substantially better than n squared. This is that demonstration. Merge sort went this fast. So while I am about to teach you selection sort and insertion sort, you're going to think, well, why are we doing this now that I know merge sort's so much better? Why don't we just move on to that? It's because it's important to understand how these algorithms work and how we analyze them. And that's what we're going to do today. We're going to look at selection sort and insertion sort, how they work, and how we can analyze them. So that way, when we move on to merge sort tomorrow, we have the skills to say, not just I read in a book that merge sort is better, but you can explain why merge sort is better. Because that's the key to understanding analysis of algorithms. Understanding how to take an algorithm you may not be familiar with and try to interpret what the runtime complexity is. To that end, is there ever a reason to use a selection sort instead of a merge sort? Pretty much never. I mean, you saw the runtime difference. There might be some differences with insertion sort, but that's a separate thing. We'll get to that later. Anyway, from there, let's talk about the selection sort. I want you, Twitch chat, to give me 8 numbers. 8 numbers. Do not make them in ascending order. Each person post one number between 1 and 100. Positive 1 and 100. Give me 8 numbers. $21, $39, $78. 21, 39, 78. 17, 58, 74. And 44 and 56. Thank you. Perfect. All right. I'm going to sort these using a selection sort. Now, the idea of a selection sort, it's called selection because I am going to repeatedly select the minimum. I'm going to repeatedly select the minimum and move it to the front. The way I find the minimum is first I'm going to assume the minimum is my first value, is 21. I'm then going to iterate through the rest of the list, and I'm going to look for any value smaller than that. So 39 is not smaller than 21. 78, not smaller than 21. 17 is smaller than 21. So 17, and then I'm also, in addition to keeping track of the minimum, going to keep track of the min index. That is the index of the minimum, which is now index 3. So the minimum is now 17. I'm then going to keep going. 58, not smaller than 17. 74, not smaller. 44, not smaller. 56, not smaller. So this min index is 3. I'm going to swap the values at index 0 and index 3. I'm just going to swap them. And so I swap them by first creating a variable called temp. I'm going to store the value at index 0 into temp. That's 21. I'm then going to copy the value of the minimum into 0, into index 0. So that becomes 17. Then I'm going to, at min index, insert the value temp, 21. So all I've done here is I've swapped the two, but I need this third variable in order to do the swap. At this point, everything to the left of this line is sorted. Now, that's not a very big accomplishment, right? We've only sorted an eighth of the list. But let's keep going. Now that index 0 is sorted, I'm going to say I equals 1. That is, I'm finding the minimum from 1 until 7. I loop through, I find the minimum is 21. So I swap 21 and 39. Now everything to the left of this line is sorted. I increment I equals 1. I find the minimum. 39 is smaller than 78. 58, 74, 44, 56, all larger than 39. So I swap 39 and 78. I find the next minimum. 58 is smaller than 78. 74 is not smaller. 44 is smaller. 56 is not smaller. I swap 44 and 78. Now everything to the left of here is sorted. And I keep repeating this. So 56 is the next smallest, so I swap 58 and 56. Then 58 is the next smallest, so swap 58 and 74. Then 78 and 74 are out of order, swap them. And now I'm done. The entire array is sorted. So I keep repeatedly selecting the minimum and move it to the front. That's a selection sort. And it turns out the code for this is fairly straightforward and, in fact, relatively easy to explain. Here is actual working code for a selection sort. Selection sort loops through the array starting from 0 up to but not including the last element. We assume the minimum is the value at I. We assume the min index is I. We then loop through the rest of the array. So I plus 1 until the end of the array. And if we find a value that is smaller than the minimum, we update the minimum and the min index. At the end, we just swap the values in the array at I and the min index. Don't worry about this print thing. This is just part of my program. It's whether or not you want to print the output. And then we keep repeating this overall loop, mainly this part, until I is the second to last element, at which point that's our last time through the loop. So this is the selection sort. Just find the minimum. That's what this loop does. This loop finds the minimum, and then swap the minimum into position I. Any questions about the selection sort? The swap method is not scary. The swap method is this. Remember how I said I create a temp variable? I store array j into the temp variable. I then store the value at I into j, and then I copy the temp value to I. That's all it is. The swap method is just that. The issue is you have to do it that way because let's say I wanted to swap the marker in my left hand with the stapler in my right hand. I can't just say, oh, we'll put the marker in my right hand. Because by doing that, I have to drop the stapler, and now I can't pick the stapler up. It's gone. I've lost it. So I have to create like a third hand, which I'm just going to treat as like my neck. And it's the idea of I put the marker in my temporary variable, I then switch hands, and then I grab the marker. You need a third hand, effectively. So that's why it has 3 variables. The swap method is fairly simple. I mean, I could have easily written that code here, but it just makes it's easier to explain, like, this is just where the swap occurs. Again, I'm trying to make my code dry. Don't repeat yourself. Alright. Now the insertion sort. The insertion sort... Well, actually, before we do this, before we do the insertion sort, before we do that, let's analyze this algorithm. First, at a code level. Let's analyze this algorithm at a code level. And fairly straightforward, you'll see. Here I am looping over almost the entire array. If the array were size n, this loop runs n minus 1 times. And here I'm looping from I to the end of the array, which in a worst case is n times, n minus 1 times. So these are nested for loops, each of which in a worst case are size n, so that's O of n squared. From a code level, that's fairly easy to see. Now let's analyze the selection sort from an algorithmic level, talking about finding the minimum. So the first thing is, I have to find the minimum to put into the first value. To find that minimum, I have to search 8 values. That is to say, I need to make 7 comparisons. Here's why. I can find the minimum between these 2 values. And then whatever the minimum is, I'm going to compare to this. That's 2. This, 3, 4, 5, 6, 7. So to find the minimum between 8 values takes at minimum 7 comparisons. 7 comparisons. After I found the first minimum, I then need to find the minimum that goes here. And there, I have to compare 7 values, which takes 6 comparisons. And then the next one, 5 comparisons. And then 4, and so on. There's a famous mathematician, Gauss, who when he was a kid, his teacher thought he was like a little smartass. And his teacher said, all right, you have to sit in the corner and add up every number from 1 to 100. And I don't want to hear a peep out of you. And before she finished the sentence, he said 5,050. Because it turns out there's a formula, because this is 7 plus 6 plus 4 plus 3, ... plus 1. The sum of every number from 1 to 100. That sounds like a lot of work. 1 plus 2 is 3. 3 plus 3 is 6. 4 plus 6 is 10. But you don't actually have to do it that way. Because what you can notice is if you do the sum of any series, 1 plus 2 plus 3 plus ... and then I'm going to write plus 98 plus 99 plus 100, it's worth noting that 1 plus 100 is 101, and 2 plus 99 is 101, and 3 plus 98 is 101. And now I have 50 ways to get to 101, which is 5,050. The formula for this, therefore, the formula for the sum of every number from 1 plus ... plus to n. The formula for this is therefore 1 plus n times n over 2, or 1/2 of n squared plus 1/2 of n. And this formula is O of n squared. So the sum of every number from 1 to n is O of n squared. So that's how we arrive at selection sort being O of n squared. No matter how you write the code for O of n squared, it's going to be, or excuse me, no matter how you write the code of selection sort, that code is going to be O of n squared if it is a selection sort. 101 choose 2 also works. That is correct. But that's, that's in this case, I just wanted to get to this. If you ever see this sequence, this should immediately make you think O of n squared. That's immediately what you should think. Insertion sort, in a worst case, evaluates exactly the same. So let's talk about the insertion sort. I'm going to need more numbers. I need 8 more numbers. Again, please don't give me ascending order. Just give me 8 numbers. 1 to 100. 5, 60. I'm not going to do 5 first. I'll do 5 over here. 66, 26, 13, 76. Give me larger numbers. Numbers larger than 50. And let me move the 5 over to here. And the 13 to here. 67. That's a good one. 88, 77. All right. For this one, I'll just do 50. And let me swap the 5 and the 18, actually. For the 88. Okay. So if this is my set, here's how the insertion sort works. It's going to sound similar, but there's a difference. I'm going to assume that everything to the left of this line is already sorted. Because every list of size 1 is sorted. So 66 is sorted. I'm now going to add the next value in the array into sorted order. So I'm going to put 26 in order with 66. And it turns out that if I compare 26 to 66, they're out of order, right? 26 is less than 66, so I need to swap them. So I swap 26 and 66. And now the values are in the correct order. Well, now I need to bring 67 into the correct order. Except, it turns out that I'm already done. Because 67 is greater than 66, therefore it's already in order. I don't need to fix it. Now we look at 5, and 5 is clearly out of order because 5 is to the right of 67. It shouldn't be. So I'm going to swap them. So 5 swaps place with 67. Then I need to compare 5 to 66. Oh, it's still out of order. Swap 5 and 66. Then I need to compare 5 to 26. They're out of order. Swap 5 and 26. Now there's nothing else to compare 5 to, so I'm done. Everything up to here is sorted. I then try to put 76 in order, but 76 is 67, to the right of 67, and I want to notice I never have to compare 76 to any other number. I immediately say 76 is greater than 67, and I'm done. I don't ever mathematically need to compare 76 to 66, 26, or 5. I don't need to do it. From there, 50 to 76, well, it's out of order, so I'm going to swap them. 50 to 67, out of order, so I swap them. 50 to 66, they're out of order, so I swap them. 50 to 26 are in order, so I stop. I see a question. Is it kind of like adding to the rear rather than the front? Exactly. So rather than finding the one value to swap, I'm just integrating each value in one at a time and finding the best place for it. So now everything to 76 is sorted. 88 is greater than 76, so I don't need to do anything. Now 13 and 88, I would need to swap 13 and 88. I would then need to swap 13 and 76. I then swap 13 and 67, then 13 and 66, then 13 and 50, then 13 and 26, but I would not swap 13 with 5. So I would just keep swapping it until it found its right position. Now, doing this, the insertion sort is still, in a worst case, O of n squared. If the list were in complete reverse order, that is descending order, it would actually take n squared steps. But the insertion sort still tends to be faster than the selection sort, because with a selection sort we have to do n squared, or half of n squared plus half of n comparisons. We have to do it. There's no way around it. With the insertion sort, we may need less than n squared. Now, that number will still be proportional to n squared. And in a worst case, it is n squared. So we say insertion sort is O of n squared. But insertion sort is a bit better than selection sort. However, if I double the size of my list, insertion sort is still expected to quadruple in runtime. So it's still not great. Here's the code for insertion sort. It's a little bit harder. Again, this code is uploaded, so you can look at it at your own. The idea is I'm going to loop starting from I equals 1 rather than 0. I'm then going to loop backwards from I to 0. If I need to swap, I perform the swap and then I keep looping. But if I don't need the swap, then I break. I stop looping, the inner loop, and then I move to the next I value. So that's the insertion sort. Are there any questions about that? Any questions about the insertion sort? Or the selection sort? And again, we have, well, we'll do these activities afterwards. All right, so let's do a couple activities. Let's do pseudocode for a problem. Let's say I want to get the sum of integers, and I want to devise an algorithm that will take a list of s integers and some other integer x, and it will determine if two integers in the list s have a sum that is exactly x, and only two. Try to come up with an algorithm, and I encourage you to jump in the Discord and work with each other on this. This is not the daily activity, but this is an activity that I want to do just to get some practice. Try to come up with this algorithm and determine the algorithmic complexity. So everyone should be, I should be seeing a lot of people in Discord working with each other on this. I only see one so far. So congratulations to Catalina for being the good student. I know, I haven't given you enough time. But see if you can work out an algorithm for this. I'll give you a couple minutes, and then I'll come back with my solution. And we'll see who came up with the best algorithm, or if anyone can break the naive solution. So again, you have a list. We'll say an array list, if you prefer. An array list of integers. And we want to determine if there are two integers whose sum is x. How would you do that? And what would be the runtime complexity of that? Now, I don't need exact code. I don't need Java code. It can be pseudocode. You can describe the algorithm, and I'll do pseudocode. So I'll give you another 2 minutes on this. I'll give you until 2:59, and then I'll give my solution. We'll see if anyone can beat me. So David, that's a valid solution, yeah. But we'll see if anyone else comes up with different solutions or pseudocode. We'll be right back. All right, we're back. So, does anyone want to? So we saw David share their solution, and I think that's a way to word it. Let me try to word one this way. Let's try this. For int, we'll say I in S. So this is how I would write the pseudocode to David's solution, or the Java code. If S dot contains, and this would be X is the sum minus I, return true. And if I loop through the entire list and never find it, return false. This would be a valid working solution, and I think that pretty accurately sums up what David suggested. What is the runtime complexity of this solution? What is the runtime complexity of this solution? Anyone? Well, it's not O of n, because remember, contains is not constant time. So while we only have one loop, explicitly, remember that contains is O of n. So this is an O of n inside of an O of n, ergo this solution is O of n squared. Now, did anyone come up with a better solution they think? Did anyone come up with a better solution, maybe? I will say I will be surprised if you did. So to my best knowledge, there is no better solution than O of n squared to this problem. If someone finds that I'm wrong, let me know. But I don't think... Yeah, you could have come up with a worse one. That's possible. But not a better one, I don't think. If someone really thinks they did, come to me in office hours. And if you're correct, I will explain your solution. I can't think of a better one. I think there's no way to do this better than O of n squared. So here's one. This one's pretty tricky. I have a list of two-dimensional points, x and y, and I want to determine if there are at least, given a list of points, like this, is there at least one set of collinear points? That is, are there 3 points in a line with each other? Are there 3 points in a line with each other? How would you go about that? Talk to each other a minute, see if anyone can come up with a solution. By the way, when I look in Discord, I can see that literally everyone is muted, so people aren't talking, and that's not fun. So this is actually a pretty common problem, some kind of imaging you need to do. So here, I want to see, are there any points that are collinear? So work with each other on that. I'll be back in, let's say 4 minutes. So I'll give you to 3:07. See what you can come up with. To be clear, collinear does not mean the same point. It just means, are they in a line with each other? That is, does the line that passes through these 2 points also pass through the other points? All right, we're back. So with that, Here is what I would call the naive solution. And naive not meaning any negative connotation, just meaning making the fewest assumptions. I would say first, for point x in points, that is, for each point, I'm going to look at for point y in points not equal to x. And I could put some logic there, but this is still a for loop. So for two different points, x and y, I'm going to get the slope between x and y. Sorry, I lost the screen. For each point, I'm going to say, okay, get the slope. So, slope between x and y equals, and it's just x dot x minus y dot x divided by x dot y minus y dot y. It's pretty standard geometric slope. Or, hang on. There we go. I get the slope. I am then, for every point z that is not equal to x or y, I would say something like, if, and I would calculate, well, so I would calculate, this is the slope y. So this is the slope x to y up here. Slope y. Slope z is the same calculation, but instead of using the point y, I'm going to use the point z. So slope z is this. And if slope x equals slope y, or excuse me, not slope x, slope z equals slope y, then that means these 3 points are collinear. So I would return true. So this is my naive solution. And let me widen it a bit so you can see it. So given what I've written, this has a fairly trivial runtime complexity. What is it? Anyone want to guess what the runtime complexity is? N cubed. Right. It is O of n cubed. Because I have a loop over the points, a loop over the points, and a loop over the points. Sorry, my indents are a bit weird. This is O of n cubed. My indents were a bit off. But this is very much O of n cubed. Again, this is pseudocode. It's not designed to be incredibly formal. Alright, so here's the thing. This is not the best solution. Here's what I'm going to do. For every point x in points, make a list of the slopes to every other point. So that this is already a nested loop, right? Because I have to say, for point x in points, I'm going to make a list or a list double slopes equal new array list integer. I am then going to say, for point y in points, if y does not equal x, then slopes dot add y. slopes dot add, not y, excuse me, slope xy. Again, let's assume this is a function that just calculates the slope from the point x to the point y. And as we talked about, the best sorting is O n log n. And so then I will do slopes dot, or collections dot sort slopes after the for loop is over. So I find the slope of x to every other point. I then sort that list of slopes. At that point, iterate through slopes, and if two adjacent values are the same, that means that x has the same slope to two different points. And they would have to be adjacent because I sorted. So iterate through the slopes, and if two adjacent values are the same, return true. And if I get to the end of this for loop having never returned true, I return false. This solution also works. Now this one's a bit trickier. Break down the loops. I have this nested loop. I have this one, which we know at worst is n log n. If we do a merge sort, which we don't know how merge sort works yet, but merge sort is n log n. And then this loop... Sorry, my keyboard doesn't want to seem to participate. So if this is my algorithm, well, this loop is O of n, this is O of n log n, and this inner loop is O of n. So the way I would work out the runtime complexity is I would say, okay, my outer loop takes n steps, and that is times n for this loop plus n log n for the sorting plus n. That means if you work this out, it's the same big O complexity as saying n times n log n, or n squared times log n. That is to say, this approach has a lesser complexity. Now, if you don't follow it entirely, don't worry. I'm not going to be testing you on this particular problem. But what I'm trying to show is by using my understanding of sorting, I can actually make this problem faster than our O of n cubed solution up here. Using data structures, using a set, I could make it O of n squared. If instead of this being a list, I made this a set, all I would need to do, I wouldn't even need this. I would just say, if this is ever false, if I try to add the slope and it's ever false, that means I found a slope that is already in the set, and I can return true. And at that point, this solution is O of n squared. And that's actually the best solution. The best solution to the collinear problem is O of n squared, which is substantially better than O of n cubed was. So if I went from O of n cubed to O n squared log n, let's say n were size 100,000, it would take this many, a quadrillion operations to do the n cubed approach. N log n, it would take only 166 billion. N squared, it would only take 10 million. So the best solution, and I don't have it here because I actually didn't know the O of n squared solution when I wrote these slides, but there is an O of n squared solution. This is it. It's a hash set, that's the key. A hash set. Then that is O of n squared. Again, I'm not going to throw anything nearly this tricky at you in this class on the exam. This is something you'd see in like algorithms or maybe 2150. If it were late in the class in 2150. Point being, always look for the better solution, because the most obvious solution is not always the best one. So we're out of time. I'm sorry, I went 2 minutes over. I'll cut it off immediately. We will pick up with recursion tomorrow. The quiz is up. The daily activity is up. I will see everyone tomorrow. I'm sorry I ran 2 minutes over. I actually just lost. I forgot to set my alarm. I usually have an alarm that goes off 1 minute to go, and I forgot to set it. So apologies. Take care, everyone. Now to answer the question I got earlier, which has nothing to do with lecture at all. This is a Stream Deck, and the idea is all of these buttons are programmable, so I could program them to do, did you go over the critical section for the DA? What is the DA? Can you clarify what you mean by the DA? Oh, the daily assignment. So the critical section is the section of code that gets repeated the most. So for example, in this pseudocode, the critical section is this, because it's the thing that is inside of both loops. Up here, the critical section is here, because it's the thing that is inside the most loops. So that's what we mean by the critical section. So we consider often the runtime is how many times does the critical section run, assuming the critical section is all constant time operations. If it's not, we need to take that into account. Anyway, the person who asked, so this is just a deck that I can set up and program. So I can program things like this would be my starting screen, my ending screen, webcam, etc. I can program mute buttons or even sound effects or whatever. The point is, it's just a miniature programmable keyboard. Because right now, if I want to mute myself, what I do is I hit Control-Shift-S. And if I do this, now you can hear me speaking. But it's multiple hotkeys. And this approach will be easier. That's the hope. You don't see the new quiz up yet. Let me look at that. Oh, I did actually forget to publish it. It is up now. It is now up. The quiz is available. Also, the nice thing about this is each of these can actually be a light. So you can put like a visual cue. So like I could put like a microphone symbol being crossed out for like, this is the mute button. The key is I can put onto these buttons, they will show me what the button does. So it produces the visual feedback instead of memorizing hotkeys. So that's why it's cool. I think it'll be very useful for teaching. As well as I do casting sometimes. And not on this channel, obviously. And, it'll be fun for that too. So. Alright, that's all I got. I just wanted to show that because someone asked earlier, but I knew it would take a bit to explain, so I didn't want to take time out of class to do that. Alright, I'll see you all tomorrow. Take care.